Okay, so now we're going to talk about a different way of calculating heat. So what we did before was using specific heat and temperature change to talk about the heat that's involved, generally speaking, with metals and water and things like that. Well, what we're going to do is we're going to expand it to include the heat that's involved when you do a phase change. So we're talking from a solid to a liquid to a gas, or from a gas to a liquid to a solid. Now remember, these are reversible reactions. This one is endothermic. It takes heat to make this change. But when the gas condenses or the liquid freezes, that's an exothermic reaction. They're reversible in terms of amount of the energy you get out. So anytime you have a phase change, it involves the exchange of heat. A phase change occurs at the melting and freezing point when a solid melts, so that would be going from a solid to a liquid, or a liquid freezes, liquid to solid, like I said, endo, exo, okay? And it also occurs at the boiling point or the condensing point when a liquid boils, that's endo, or a gas condenses, that's exo. And so the amount of heat that we can calculate, you can calculate the heat, but the thing is, during a phase change, there is no change in temperature, and that's kind of a weird concept. And if you think about it, this is what my little chunk of ice looks like. So here's my little ice molecules. Water. It's very solid. They're stuck in one place. In order to turn into a liquid, they have to move apart from each other and start sliding around. Remember, we're talking kinetic energy there, okay? And so to get them from the point where they're stuck in one place to the point where they're sliding apart, we have to add energy. But all that energy does is it breaks the ice particles apart into molecules where they're able to move around. And so there is no change in temperature. It doesn't increase the temperature of the mixture. All it does is it changes it from a solid to a liquid. And the same thing true is when it's boiling as well. So all the energy that is absorbed in melting and boiling is used to break apart the particles from a solid to a liquid, or a liquid to a gas. And again, this is reversible. If we're talking about a liquid freezing, all the heat that is involved that's released allows the liquid to slow down and stick together and become a solid. Same thing with condensing. So it does take much more heat to melt a solid at its melting point than to raise its temperature once it's melted. And when it changes from a liquid to a gas, that's way more heat, because not only is it moving faster, but they're completely flying apart from each other. So it takes a lot more heat to make that happen. So there are equations for calculating the heat change. So again, we're talking Q for a phase change, but it's slightly different because it doesn't involve temperature. So what the equation looks like for melting and freezing is Q equals the mass, but we don't have C and delta T because it's not changing temperature. Instead, we have a constant, and it's called the heat of fusion. And for boiling and condensing, again, heat equals the mass, but again, we can't have specific heat and temperature change because there isn't one. So it's called heat of vaporization, and we'll talk about the definitions on those. So the heat of fusion is the amount of heat that's absorbed by 1 gram of a solid substance as it melts from a solid to a liquid at the melting point. The units, therefore, are joules over grams. Degree C is not part of it because it's not changing temperature. The heat of fusion is also the same value is the heat released when the liquid freezes. So for water, it's 333 joules per gram. For the melting and for the freezing, it's for both values. It's a constant value. And so do you determine the heat absorbed or released at the melting or freezing point, you're just going to take the mass and multiply by the heat of fusion. And I'll give you those values. Boiling and condensing, it's called the heat of vaporization, and it's the amount of heat necessary to vaporize 1 gram of a liquid into a gas at its boiling point. Again, the units are joules per gram. And when you're talking about water condensing or steam condensing or a gas condensing, it's the same value. And for water, it's 2260. Okay, significantly more energy than the 333 that we saw before, almost 10 times as much. And that's because it takes more heat to make a liquid boil. And so here's again the equation. So sample problems, and this is where we're going to start doing some math. So calculate the heat required to melt. That means our equation is Q equals mass heat of fusion. So Q equals the mass, 87.2 grams, multiplied by 255 joules per gram. All you do is you multiply. And sometimes the units are very helpful because they can tell you what you need to do in terms of solving, because I know I need joules at the end, and grams are going to cancel out. So 22,236 joules. Okay, so that's a reasonable amount of energy, but melting does take more energy than just raising temperature. So now we're talking about the heat released, but again, still Q, and we're talking about a gas condensing. So we're going from a gas to a liquid, and we're going to use Q equals M, heat of vaporization, because it's condensing. So the mass is 135 grams. The heat of vaporization is 3105 joules per gram. Multiply them out, and this is going to be a significantly large number because it's changing temperature, or it's changing phase at the boiling point. So 419,175 joules. And again, I'm not so worried about it. If you called it 419,000 joules, that's fine, because a joule really isn't much of anything. Now, what happens when you combine a phase change and a temperature change? So we're not just talking about a solid melting, but we're talking about a solid melting and then the temperature increasing. So when you add heat to a solid that's below the melting point, all the heat is used to raise the temperature of the solid up to the melting point. So we're talking a delta T on that one. So Q equals MC delta T. But once it gets to the melting point, there is no temperature change. And so we're going to use the heat of fusion on that one. Then once it's all completely melted, you can continue to add heat and it will raise the temperature. So again, we're doing a delta T, and the temperature is going to go up until it hits that boiling point. So there's your Q equals MC delta T, but once it hits the boiling point, there is no temperature change. And so the equation is a little different. Q equals the mass times the heat of vaporization. And then once it's all boiled again, we're looking at a delta T. So you can pay attention to what's going on in terms of physically what's happening. But it's hard because there's so many different equations. You have this one, and then you have the heat of fusion one, and when should you use, and when do you use it? And so what you're going to do is you're going to use a diagram to illustrate the phase changes and the temperature changes. So this is what a phase diagram looks like, and this is for any substance. Okay? If you start with a solid below the melting point of whatever the solid is, and you add heat to it, it's going to increase in temperature. So here you have a delta T. So Q equals MC delta T. But when it hits that melting point, the temperature doesn't change. Even if you are applying heat, the temperature stays constant. This is temperature right here. And so the Q equals the mass times the heat of fusion. But once it's all completely melted and now it's a liquid, so this is melting. Once it's all completely melted and you continue to add heat, the temperature is going to rise. So Q equals MC delta T. But once it gets to that boiling point, again, all the heat, you're still applying heat, but what's happening is it's going to boil. And so the temperature doesn't change. It's constant. Q equals mass times heat of vaporization. And then once it's all done boiling, and it's a vapor, temperature is going to continue to increase. If you continue to add heat, Q equals MC delta T. So you've got 5 different things going on, and it helps to draw this picture with temperature on the y-axis, heat along the bottom axis, and the way you calculate the heat depends on what's happening. If it is increasing in temperature, it's that equation. If it's changing phase, it's a different equation. And then to find the total heat, you just add them all up. So ethanol has a melting point of negative 114, and I'm giving you a specific heat for it at a bunch of different numbers. How much heat is needed to change that mass from negative 195, so it's well below the melting point, to a liquid at 25. So I'm going to draw the little picture. Temperature over here, heat on the bottom. And the way you do this is you look at the lowest possible number they give you in the problem, negative 195, and you're going to put that at the bottom somewhere. It doesn't have to be drawn to scale. And then the highest temperature they give you, put that at the very top. Okay? Now, any other temperature they give you in there, I would put it inside. So the negative 114 goes here, somewhere in the middle. Again, it doesn't have to be scale. And so now you have to interpret from that. You're starting with a solid, and this is my melting point. So the temperature of my solid is going to go up until it hits that melting point, at which point it is going to melt. And if I continue to add heat, once it's all melted as a liquid, the temperature is going to go up until it hits 25, because that's where I'm stopping. So what I have here is I have 3 different kinds of calculations. So the Q for the solid part is the mass, 51.5, times the specific heat for the solid. Make sure you use that right number, 0.97. And then the temperature change for my solid, well, it went from negative 195 to negative 114. And so I'm going to get out my calculator, and I'm just going to subtract it. And so I get a positive number, because that's all I'm looking for is a temperature change of 81. So I'm going to get that heat. And then I'm going to do the heat for the melting. And again, the melting is the mass, 51.5, times the heat of fusion up here. This is Q equals mass heat of fusion. This one is Q equals mc delta T. And the heat of fusion is 109. And so I'm going to get a number there. And then I'm going to do the Q for the liquid part. And because it's changing temperature, Q equals mc delta T. So 51.5. And I'm going to use a different C this time because it's a liquid, 2.44. And the temperature change. Now this is a tricky one because it's going from a negative 114 up to 25. That means it's passing through 0. So negative 114 to 0 is 114. And an additional 25 makes it 139. Okay, so I'm going to do those numbers. And I'm just going to round them to whole numbers because it's just easier that way. So 4046 joules to raise the temperature of the solid. And 5614 joules to melt the solid. And 17,467 joules to raise the temperature of the liquid. So the Q total is those added together. And it looks like that's about 27,127 joules. Okay, so drawing the picture helps because then you can kind of identify what's going on when you're doing these problems. So now, calculate the heat needed to raise the temperature of 25.5 grams of ice starting at negative 37. So we're going to draw the diagram. Lowest temperature is negative 37. And it's going all the way up to 125 degrees. Now with water, I will expect you to know that water melts at 0 and boils at 100. Okay, so in terms of this picture, it's starting at negative 37 as a solid. It's going to hit 0, it's going to melt. Once it's all melted, it's a liquid, and it hits 100 degrees, then it's going to boil, and then it's going to raise temperature as a gas. So I have 5 different calculations going on here. Anytime there's a temperature change, Q equals mc delta T, here, here, and there. Where it's changing phase, though, Q equals mass heat of fusion or mass heat of vaporization, depending on whether it's boiling or melting. So 5 different calculations. I'm just going to set them up. Q for the solid is 25.5 times the specific heat of the solid, 2.06, and the temperature change of the solid is 37 to 0, 37. That's one of the nice things about water. Q for melting is 25.5 times the heat of fusion, because it's melting, 333. Q for the liquid is 25.5, and now I'm going to use the specific heat for the liquid, 4.18. And the temperature change just for the liquid is 0 to 100. And I'm not going to actually solve these. I'm going to just get the total. For boiling, it's heat of vaporization, so still 25.5, and now it's 2260. And the Q for the steam gas is 25.5. The specific heat for the steam is 2.02, and the temperature change just for the steam is 25. So I'm going to pause the movie. You guys can solve this one. Okay, and it looks like on my calculator I get a Q total of 80,011 joules. Okay, so it's not that complicated, but you really do have to draw this picture.